Yeah,
And they're
that
very
makes
good for
sense.
that. Very, very good for that.
So then, as far as the spectrum goes, as you kind of alluded to, every piece of the spectrum does something different. Some of the
Mhm.
spectrum we probably have no idea yet. We're still looking at those things. So can you briefly kind of run through what we're looking at as far as what each section of the spectrum do, and then maybe we'll get a
Yeah,
little bit more into
yeah,
detail.
yeah, sure. If we start off with our long wavelengths we've just gone through, we've got our infrared and our red light, and they actually penetrate the body of an animal quite well, particularly the short wavelength infrared that will penetrate right through. I think we've pretty much covered that. But also, red and infrared A have biological effects. It's not just warmth. And I think that's something we tend to completely forget. We tend to forget that it isn't just heating when things are thermoregulating, because red and infrared actually work on cells, and they work on an enzyme called cytochrome C oxidase, which is in skin cells. And it actually upregulates over 100 genes. And they're very important for things like controlling cell growth and wound healing. They change the way the immune system works. They promote the immune system for protecting against things like UVA damage, in fact. So it's a sort of a healing light. People talk about infrared as being a healing light, and it really is. And it's used a lot in medical technology using low-level lasers and things like that. But I think it's one of the reasons why wild animals heal up so well in the wild, and they're using this natural light for heating. And we move down the spectrum a bit to our visible light, visible perception, and we have to think about the way the reptile eyes work. Our eyes have got 3 cones. We've got 3 cones that respond to different colours in the back of our retina. And there's a blue cone, well, they say blue, it's responding most to blue light, one that responds most to green light, and one that responds to sort of orange and red. And we decide what colour a thing is by the way they overlap, so that if the brain sees a mixture of this particular amount of the green stimulation with the same amount of red, we go, oh, it's a red colour. And that's how we determine colour vision. Well, reptiles are slightly different, and different species of reptiles are different as well. So if we take, say, the turtle, it's got the same 3 cones, blue, green, and red, but it's got a 4th cone, which is responsive to UVA. So this turtle has a very wide range of colour vision, right through from UVA, right through to the borderlines of infrared. So it's actually got, if you like, it's got wider colour vision than humans have. So, full possibilities of full colour vision there. You can definitely see red. But if we look at other species, they can vary. Geckos, for example, light in twilight is mainly from, after the sun has gone down completely, it's mainly from diffuse light in the sky. So you get more of a blue under UVA light, because that's what's reflected in the sky as it gets darker. So they have very, very good vision in that range of light. They can differentiate because all 3 of their cones will register into the blue and infrared, into UVA rather. So you get very, very good colour discrimination in that type of wavelengths. They can see into red, but they can't necessarily discriminate much colour there. If we look at snakes, again, they vary hugely. Garter snakes don't have any night vision rods, they only have cones. So their best vision is in daylight. And again, they've got very good vision in UVA and right through to red. So they've got good colour vision, which is why some of them are very highly coloured as well. But if we look at things like the boa, which is the more nocturnal activity, that has a very reduced, it only has two colour cones. It's also got a good number of rods for night vision, which have a sensitivity somewhere in the blue-green. So that can see very well. It can see very well in dusk because it's got the UVA and it uses the rods for that. And it can also see some of the greens and reds, but probably it's colorblind in that sense. It's like red-green colorblind. So you've got a huge range of different colours that animals can see or not see, or determine what the colour, specifically what the colour is. They can see the light, but they don't know anticipate what colour it is. So we have to be a bit careful when we provide lighting. We really need to provide a full spectrum of sunlight because that's what it's evolved to use. And if we change the colours and alter them, then the animals are losing out. And there's just my little example there is people sometimes say to me, well, can I just use red lights for heating and lighting? And you think, well, you're wiping out all of its colour vision because everything is either red or shades of grey or black. And particularly if it's got any UVA reflective parts, then you're removing the ability for it to see those as well. So basically, full spectrum light is really important. Before we move away from the UVA thing, everyone goes on, we don't know much about the UVA, we don't measure it. But it also does have biological effects. It increases nitric oxide in the skin. It's a defense reaction. That increases vasodilation. It makes the blood supply better, and it also lowers the blood pressure. So there are things that we don't know much about, which could be quite important. But before we move away from visible light altogether, I think we should just talk a little bit about this non-visual perception.
Because this blows my mind. When I first read this from, I think it was a section of a textbook that you had written a snippet in, and I couldn't believe this. So please go ahead with that.
Yeah, this is what's going on in our brains and in animal brains that really has only been discovered for perhaps, I don't know, 15, 20 years. And how it works out is that we've got different photopigments. These are the photopigments that we're very familiar with. These are our cones that we see colour with. But also at the back of the retina, in the ganglion cells, we've got cells which respond differently. They have a different pigment. It's called melanopsin. And it's a non-visual pigment. It doesn't signal to the brain that they can see anything, but it sends signals to parts of the brain that are responsive for circadian rhythms, for all that kind of out of sight, out of mind responses to light. And it's mostly responsive to blue. It's highly responsive to blue. Everyone goes, well, why is it blue? And it's probably because blue light is one of the signals of daytime. When the sky changes from being dark at night to just before dawn, you get the diffused, the refracted, what's the right term, scattered, the Rayleigh scattering of the sunlight coming up, and it comes through as blue and UV. And so, although it's incredibly dim, so you can't really recreate it in a vivarium, but that incredibly dim blue light stimulates these little cells, and it goes, oh, it's daytime. And that signals to the brain that dawn is coming, and likewise the opposite at the other end of the evening. And if I just do this little diagram of this is an iguana. The light doesn't just go into its eyes, because reptiles also have these photoresponsive cells with opsins, like melanopsin, in other parts of the brain as well. And so that the light's going through the lateral eyes, the normal eyes. It's also going through, for the species that have got them, through the parietal eye, and the sensors in that are responsive to blue and green. And also light through the skull. And I don't know if any of you have ever held up a leopard gecko to a bright light. You can see right through the head, through the eyes. But when you think about these tiny animals, you hold them up to the light and you can often see the organs through them. So the light's going right through the body of a small animal like that. So it's not really surprising that they've made use of that by having cells inside the brain. So if we just go inside his brain, here they are, here's his brain. Here's just the brain. And we've got the lateral eye, we've got the third eye, and we've got underneath in the skull, you've got the little third eye, and you've got the pineal body, which is the area which produces all the hormones. And you've got the SCN, I can never say suprachiasmatic nuclei, which is a little group of cells, which is the clock setting mechanism in the brain. And you've got these tiny little photoreceptors lying in the ventricles of the brain. They're all responding to light. So the signals come from the light and feed into the SCN, and then that feeds back a loop into the pineal, which is the main organ producing the hormones and the neuroendocrine network. So you've got an amazing system that's responding to the intensity of light, the wavelengths of light, and telling the brain what time of day it is and how bright it is and what season it is, because how long the day length is. And it needs to be bright enough. The light that we give them needs to be bright enough to stimulate the brain in this way. And when you think about it, if you put a dim light over it, there's not an awful lot going to get through the skull. Whereas sunlight is incredibly bright and goes right through the skull. So we do have to also think about the intensity that we're producing. This is Quinn Harris's little picture, which he puts up on the forums. It's absolutely wonderful. He went outside with his camera and took a photograph under an overcast sky and also measured the lux, and he got 40,000 lux. He then didn't change the camera settings. He left them exactly the same. And he also measured the lux in his vivarium for his beardie, and it was 4,000 lux. So that when he compared the photographs, he went, oh my gosh, it's really dim in there.
It looks like nighttime almost.
Yeah, because our eyes, immediately, our pupils dilate and we see it as bright. If you walk into a dim room and your eyes get used to it, you think it's bright. And certainly the beardie's eyes will do that as well, but his brain won't, because his brain can't open up the way our pupils do. So he sees that, his brain sees that as really dim. And I think that's something that we haven't really got to grips with yet in our animal husbandry. We can increase the light quite a lot. And then finally we go right down to the bottom and we talk about vitamin D. So I don't know if we want to talk about that now or...